So question 7, this is a big question, and it's the Carnot cycle. In something like this, it's a 4-step cycle where you started at, when you're done the cycle, you come back to the exact same values. So what that means is for the total cycle, any state functions, such as these ones, these are path dependent. But for state functions, if you end up exactly back where you started, the total value of these state functions for the cycle, the change is 0. There is no change. Okay? Whereas path dependent ones, there will be numbers that come in for the totals. So the best way to answer this question, in my opinion, and you should essentially graph it. So you're starting, let's just think about this. You're starting at 10 atmospheres and it's 600. So we'll call that point A. So you're starting at 10 atmospheres. Put a dot there. And we know that it's 600 Kelvin. So technically, you will be able to probably, we know it's 10 atmospheres. I'm just putting pressure at A, and that's volume at A. You'll be able to calculate that as needed. And you're going to isothermally and reversibly. And that's the other thing I want to draw your attention to. Notice how this one says it expands isothermally to 1 atmosphere. Call it step 1. And then adiabatic. The one thing about a Carnot cycle, all of the steps, all of them, all the steps are reversible. So even though it doesn't put the words in here, it's understood that a Carnot cycle, every single step they outline is done reversibly. Okay? So it says it goes to 1 atmosphere. So here I drew 1. And we all know that an isotherm, so call that point B, which is going to be the volume at B and the pressure at B. And if it's isothermal, you're going to still be at 600 Kelvin. And we know that isotherms kind of have a curve, a small curve like that. Like there's a little bit of a curve to it. But then it says, once from here, you're going to go expand to an even higher volume, but you're going to do it adiabatically. And it gives you the temperature only. So we know that some point C, which, you know, I don't know here how much bigger it's going to be, but I'm just qualitatively, I'm going to draw it out here somewhere. And we know that adiabatic ones, do you see how the slope of it is sort of at this angle? Adiabatic steps are always steeper. So I'm not going to draw a curve similar to this. It has to be a little steeper. So let's just put point C there. And this was step 1, right? This is step 2. And you will calculate some volume that occurs at point C and some pressure. And we know that the new information is 300 Kelvin. So think about it. Whatever you calculate the volume and pressure to be here at this temperature, reversible adiabatic expansion, you can calculate these two using those reversible adiabatic formulas. So be able to calculate that. And then part D, you compress isothermally. Interesting. This expansion is followed by an isothermal compression. So you are isothermally, but notice how it's not really even telling you, it's not telling you much about point D, but you know that, see how this adiabatic step has a steep, but you're here. You are going to isothermally, so notice this isotherm, step 1 was an isotherm at 600 Kelvin. This step 3 is an isotherm, but it's an isotherm that's taking place at 300 Kelvin because C is at 3. So I don't know. And I don't know. D ends up having a pressure a little bit more than this, as you'll find out. So I'm just going to put it, but the volume is not quite back here. So D sits somewhere like this, qualitatively. It's not exact, and it's an isotherm. So this is step 3, which is an isotherm. That's 300 Kelvin. So you'll get to point D, which will have a volume at D and a pressure at C, and we know it's 300 Kelvin. Now, to complete the cycle, we know, so it's like, that's your first step, that's your second, this is your third. You have to adiabatically go back here. Since you already know these points here, notice how you can calculate this. Because this last step was adiabatic. So if I know the final, for step 4, this temperature and these values are the final values. These are the initial. So you can back calculate VD, PD, because you know this temperature. So for the last step, these are your, like, your you know how they write down in your formulas, like V1, P1, T1. And you end up at these values. So those would become like your V2, your P2, and your T2. And if you know T1 and T2, 300 to 600, you know the VA and the PA, you'll be able to calculate these. So you can fill in this graph with all of these values. You're going to need those. So this is the first step to complete a picture on a PV graph of the Carnot cycle. And it turns out, folks, the area that's on the inside, totally enclosed, will end up being the work total for the cycle. And if I'm not mistaken, you are... Yeah, because it's reversible, the whatever that work total is for the cycle will end up equaling the negative of the heat of the cycle. That's a fact. And this is in your book when you read up on it, etc., etc. So, folks, I think we've outlined this. The other thing that you know is things like delta U, delta H. Both of these we already know because it's an ideal perfect gas. So delta U and delta H. If the temperature does not change, these are equal to 0 if ideal and no change in temperature. So step 1 and step 3 are isotherms, meaning the temperature did not change. So right away for step 1 and step 3, that's 0 and that's 0, this 0 and this 0. And the change in these for the whole cycle has to be 0, which means whatever happens in 2 will be the equal and opposite of 4 for these. Right? That's a fact. Entropy is a little different. You already know that there was a temperature change from B to C. So for instance, calculating delta U, so you could have delta U equals N CV delta T. So if I'm doing step 2, right? The change in temperature is 300 minus 600. That's your delta T. It's ideal monoatomic gas. So this, I believe, is what 3/2 R for an ideal monoatomic. And you're told you have 1 mole. So you can easily calculate delta U for this step. And when it becomes step 4, you go back from 300 to 600, which is the negative or the opposite of this value, whatever that is. And enthalpy, the formula is NCP delta T. So both hand in hand, delta U and delta H for steps 2 and 4, you can use their formulas. I got to put that in place here, sorry. Use their formulas to get values for those. So that pretty much takes care of how you go about delta U and delta H. So how do we handle entropy? Well, it turns out that entropy for adiabatic steps. Entropy. One of the biggest definitions, because right in here it's telling you, and this is interesting enough, think about it. Change in entropy of the universe. Well, if a process takes place reversibly, what is the change in entropy for the universe? It's 0. If each of these steps is done reversibly, which it is, each of these is 0 for the universe. And the total will be 0. So that is a no-brainer across there. This one, though, that's the system's point of view. So what happens to the system? And I'm thinking here for a second, how are we going to calculate? This is an interesting thing. So for step 1, what I'm interested in here is how would we go after change your entry of the system? And I think what you're going to find here, we know that the volume definitely gets bigger. It is being done reversibly. So one of the things is, we know the change in entropy of the system will be the integral, and if the temperature, it was isothermal, so we get to bring the thing out front, so you get dq reversible. But we had another formula that you already seen. Well, you know there's a volume change, and we already derived it in your notes, so we'll let you guys look that up instead of me going back for that. You had a formula in a box that looked like this. NR ln V2 over V1. So if this formula works when the temperature is constant, isotherm, which all of them here are, sorry, 2 of the steps are isotherm. Step 1 is isothermal. So you would put in VB over VA, and you would get a number. And because it was an expansion, it will be a positive number. Now, notice that it turns out step 3, you're going to notice a volume. Step 3, you're going to end up using the same type of formula. NR ln V2 over V1, which means for step 3, V2 is VD, and this one would be VC, VP. So that would be, step 3 would be VD over VC. And it does turn out to be the negative number that you got over here. So when you fill this in, step 1 and step 3 will be equal and opposite entropy numbers. Step 2 and 4 will be 0. How and why is the entropy 0? So for steps 2 and 4, delta S of the system equals 0. How do we know that? Well, first of all, one of the logical ways is looking at this. System plus. So what's going to happen, and I'll get to that in a second, but think about it. Steps 2 and 4 are adiabatic. And what that means is there is absolutely no heat transfer between the system and the surroundings. And if the change in entropy of the universe is 0 because it's a reversible process, we know that. if the change in entropy of the surroundings, it ends up being what the actual heat of a process was divided by the temperature surrounding. What was the actual heat transferred for adiabatic steps to the surroundings? 0. So this is 0. So the only way that the entropy of the universe change can be 0, and if this is 0, this has to be 0 by default. So the only way that is true, you had a formula, and I'm already forgetting it, so let's put it in this format. You had some gobbledygook with a dt plus some thing with a d, for instance, v. So think about it. For steps 2 and 4, they're adiabatic. The temperature changes, so the entropy is going to get a contribution from a temperature change. So for step 2, the temperature goes up. If the temperature goes up, this is a positive number. But the volume, it didn't go up, Mike. The temperature dropped. It went from 600 in step 2 down to 300. So because of the temperature change, there'll be a negative number for the temperature to entropy. The volume gets bigger, so it'll be a positive number, and they will be equal and offsetting to make that 0. So that's the logic behind it. So I think that basically rounds out mostly how you're going to calculate this stuff. As far as heat and work, I think I can just give you a quick look at, obviously for steps 2 and 4, they're adiabatic. So the heat for step 2 will be 0. The heat for step 4 will be 0. We know that much. Now, folks, it turns out the heat for step 1 and the heat for step 3, they're both isothermal. So what's going to happen is, whatever the heat is, it will equal the negative of the work for these 2 steps. Okay? And it turns out that you will calculate a value for all 4 steps for work. What's interesting is, in your chart right here, out of all these items, the only thing that has an actual number that's calculable is work, has an item for each one. All of the other stuff will have some zeros in there. Yeah. So how do we calculate work for step 1? Well, for step 1, your formula for isothermal reversible work, the generic formula is this one. Step 2 is adiabatic. So step 2, we know that it is equal to this. Right? Step 3 is irreversible isothermal, so that'll be the formula for that one. And then step 4 is adiabatic, so yes, it'll be U. That's a U. NCV delta T. That's how you calculate those ones. So that's step 7. Take your time, show your work, but make sure you carefully fill in this chart properly. You have to hand in, summarize your answer in a table just like that. So I can see that, makes it easier to mark.